Welcome to Wave Motion Part 1. Today we're going to define progressive waves, transverse waves and longitudinal waves and look at some important features. So a progressive wave is any wave which transfers energy or information but not matter. And what we mean by that is that matter might be a physical object such as a particle. It will not be moved by a progressive wave, whereas energy in the form of particle movements or in the particles themselves can be transferred, as can information. And these have two types. The first is transverse waves and the second are longitudinal waves. In transverse waves, the oscillations are perpendicular to the direction of wave motion / energy transfer. So you're probably familiar with these from your GCSE. If I have a rope and I move one end up and down, I create a continuous wave where these particles or the rope are moving up and down. So you can imagine that as the wave moves through, particles themselves will travel up and down, but the general motion of the wave is from left to right in this way. And so we have that particle motion, or oscillation, I should say. And that's at right angles to the energy transfer. In the longitudinal wave, oscillations are parallel to energy transfer. Or wave motion. And I think the common way that we do this is with a slinky. So if I draw my slinky, you have the chains on the slinky moving back and forward, like so. And you can also see that the energy passes down. So in this one, I have my oscillation, my movement of my particles back and forward, and my energy transfer. Actually, that's the in the same direction. So they are parallel. A good example of a longitudinal wave is sound, and transverse waves, anything on the EM spectrum, like microwaves, X-rays, etc., are good examples. So we'll look at some key features now of these two types of waves. In a longitudinal wave, you have areas where particles are close together, and that's called a compression, because the particles are compressed. And in transverse waves, in longitudinal waves, you also have areas where they're far apart, and that's called a rarefaction, where they're split up. Let's look in more detail, though, at a transverse wave. Now, we usually can represent these in graphs that show some y displacement versus some x displacement. And what we call this displacement is essentially the distance from the y rest position. So you can imagine if you have your rope, it's at some rest position, it's not been affected, and its displacement is any distance from its y rest position. So let's say I have my wave, it goes up, it goes down. I'm going to try and draw this nice and regularly. Okay, so you can imagine that as this wave is moving through, it has different displacements. At some point it's got a maximum displacement, at some point it has zero displacement, and at some point it has a maximum displacement in the negative direction. This gives us our first key definition, which is the amplitude of the wave. And the amplitude can either be from the rest position to the peak, or you can equally draw it from the rest position to the trough. So the amplitude is the maximum displacement from the rest position. Last one, we have another key feature. You can see that I have one complete wave going from here to here. That's my one complete wave. It's gone up, down, up again. And I have another complete wave. And we define the wavelength as the length of one wave. And that is given the Greek symbol lambda. It doesn't have to be from peak to peak. It can be from any point on one wave to the same point on the next. I can equally do it down here. They're all lambda. And to clarify, lambda equals wavelength, which equals distance from a point on one wave to the same point on the next.